So in the last session, we completed our topic that was lacing, backing, and column basis. We discussed two sums pertaining to lacings and column basis. Out of these two, mostly both the sums are being asked frequently in your examination, but either of these two are being asked definitely in your GTO examination. So do look at it if you have missed it. Now in this session we'll be discussing the design of flexure members, and as you know that flexure means bending, so we'll be discussing the members that are in bending under steel portion. Clear? So as we all know that bending members are generally beams, so this will be designing of steel beams that will be covering. So this design of steel beams is covered in two parts, or it's bifurcated into two parts. The first portion is laterally unsupported beams, and the second is laterally supported, or you can say laterally unrestrained and laterally restrained beams. What are laterally restrained beams? We will be discussing in the next session. Today we'll be discussing in this session about laterally unrestrained beams. That means these are generally simply supported beams that are being just placed on the columns. They are not withheld in the translation motion. Clear? So these are called laterally unsupported beams that will be undergoing. So the question here today is, design a simply supported beam of span 6 meters. It is laterally unrestrained. You always need to focus on this case, that whether the beam is for laterally unrestrained portion or the laterally restrained portion, because 70% of the design steps will be the same, but 30% may vary in these cases. So you need to remember this. It is said the beam carries a working dead load of 50 kN per meter and a working live load of 10 kN per meter. We have to use Fe410 grade steel, that means Fi equal to 250 megapascal. The beam is laterally restrained by cross beam framing and midspan. Now there is a contradiction here. The beam is actually said to be laterally unrestrained, but here it is mentioned that it is restrained as cross beam. That means we are dealing with the topic that is laterally unsupported ends. Clear? So as we have seen that the supports are laterally unrestrained, but here it is being restrained at the cross framing midspan. It is restrained by a cross framing at midspan. So if this case is being given, the question may vary only across one case that we will be seeing later on. Otherwise, this statement won't be effective in any case. Clear? That will be changed only one thing that we'll be discussing later on. So now how to solve this equation and what to solve with this equation? For that we'll be moving to page number 54 of your IS code. So pause this video and move on to page number 54. There you can see here clause number 8.2.2 is mentioned. It is for laterally unsupported beams. The main goal of our design will be to provide a section, and that section, as we are dealing with beams, it will be of I section only. So we will be selecting an I section and then we will be checking this value, that is MD, that is the design moment. If the section that we have provided carries the sufficient or the required bending moment, then the section that you have provided is sufficient and is valid. Clear? So this is the aim that we will be looking for, and for that we will be seeing these parameters that are given in your IS code. So we'll be starting with a sum. As you can see here that the loads that are mentioned is working load. So the first step will be to find the factored load of it. So the factored dead load will be 22.5 and factored live load will be 15. So the combination of these two will be given the factored total load, that comes out to be 37.5. And the next step will be always to find the bending moment and the shear force value. So bending moment here will be W square by 8, as it is a simply supported beam. So the final answer comes out to be 166.75 kilonewton per meter. And the next step will be to calculate the shear force, and shear force for it will be WL by 2. So as length is given as 6 meters, the answer will be 122.5 kilonewton. Now we have completed the analysis portion, and then we'll be moving on to the design. So for that we always have to assume something, because it is a design problem and every design problem starts with an assumption. So here we will be always assuming a trial section. That means we need to select a trial section. We need to do permutation combination, and then the section if we have selected is valid, then and then only we can apply it to our section that is for beam. Clear? So for that we will be always assuming these two cases, that is the value of KL by R will be assuming to be 100. That will be assuming this HF by TF value to be 25. Clear? So for this we will be referring our IS code page number 57 table number 14, as you can see here, the value of critical stress is being mentioned. So we will be always first finding the value of critical stress, and according to this value we will be finding the value of bending stress, and from bending stress we will be calculating the section that we will be assuming on. Clear? So for that you can see here the column value represents KL by R and the row represents H by TF value. So we always will be starting assuming these two values. So we'll be always assuming KL by R to be 100 in all cases, and we'll be assuming our H by TF to be 25. So the intersection points comes out to be this, that is 291.4. So in this case the value of FCR, that is our critical stress, comes out to be 291.4 Newton per mm square. So from this we will be moving on to again our page that we have discussed earlier. We will be moving on to page number 54. As you can see here, for lambda LT value, the equation was under root Fy by FCR. So we have completed this portion, that is we have found the value of FCR, because the ultimate aim is to find the value of FBD. FBD, as you can see here, it is xi LT Fy by gamma m0. So we need to find xi LT for that, and for xi LT you can see here the equation is mentioned. It requires the value of phi LT and lambda LT. So phi LT can be calculated accordingly, and lambda LT will be focusing on. Yeah? So we'll be going in this reverse order, and then we'll be finding the value of FBD. We won't be solving this phase, that is your right hand side column, because it deals with elastic sections, and elastic sections are not included in your current semester. So we'll be focusing only on this left hand side portion of this page. So now the first aim will be to find this value, that is our lambda LT value. This is for design purpose. We won't be solving this. We'll be using this equation that is been mentioned below. So the first case will be to find the value of lambda LT. LT, that is lateral tension. Clear? LT, that is a lateral tension, or you can say lateral. So lambda LT here comes out to be Fy was 250, FCR we just obtained was 291.4. So the lambda LT value comes out to be 0.926. Now we will be using this lambda LT value in this case, that is phi LT. So we'll be calculating value of phi LT, and for phi LT you will be needing this term, that is alpha LT, and the value of alpha LT can be solved using this page, that is our cases mentioned here. Alpha LT will be 0.21 for rolled steel and 0.49 for welded steel. As we will be using rolled steel always in this semester, we will be taking the value to be 0.21. So alpha we will be substituting here to be 0.21. Lambda LT we have just calculated, so the phi LT value comes out to be 1.005. Now we will be using this phi LT value to find the value of xi LT. So the xi LT value comes out here to be 0.716. Clear? And you always need to check this value, that the xi LT value should always be less than or equal to 1. So as we are getting the value to be 0.716, which is less than 1, so therefore our value is completed. That means the steps we have done up till now, that is these steps are correct up till now. Clear? So now we'll be using this xi LT value to find the value of FBD. FBD, that is our bending stress. So FBD will be equal to 162.7 Newton per mm square. So if in question analysis problem is been asked, then you need to compulsory use this method to find the value of FBD that we have just solved. Yeah? But for design purposes, whenever the design problem is been asked, you can opt for an alternative method that we'll be seeing now on. So for alternative method, you need to go to page number 55 of your IS code. There you will be seeing table number 13A. This table is for design bending compressive stress, but keep in mind it is for alpha LT 0.21. If you will see next page, it will be for different alpha. Clear? But here we are always using the rolled section, so we'll be always focusing on alpha LT value to be 0.21. Here in the first column you can see the value of FCR being mentioned. FCR we have already obtained, it was 291 point something. So we'll be doing interpolation between these two terms, that is between 250 and 300. So after doing interpolation between these two cases for the column, that is Fy equal to 250, we'll be getting the value to be 161.65. In manual method and in the table method, both the answer may vary, but it will vary in decimals only. It won't be issue. You can opt for any method as you like for design purpose. For analysis purpose, you need to compulsory use the previous method that we just saw. So now we will be going for our section. That means we have done these steps to identify the section that we'll be selecting, and for that we'll be using this equation. We obtain the value of FBD. Beta B can be obtained from this equation. As you can see, that beta B will be equal to 1 for plastic and compact section. We will be always assuming beta B to be 1, that is for plastic sections here. So the equation will be MD equal to ZP into FBD, and we'll be finding the value of ZPD. So we'll be making ZP as our subject, ZP, that is our section modulus plastic, that is plastic section modulus. So the plastic section modulus will be MD upon FBD. MD we have obtained by equation WL square by 8, and FBD we have just obtained. You can use any of the equation from any of the method, and the answer that we are getting is 1037.18 centimeter cube. So this is the required amount of section modulus that we will be dealing with. So from this value we will be opting for our I section, and for that we won't be referring our steel table this time. For steel portion, and in the case of beams, that means for steel beams we will always be taking the values from this page, that is page number 138 of your IS code. You will be taking the values from your IS code only. There is no need to move to our steel table in the starting portion. So as you can see, various I sections are being mentioned. We will be focusing on this portion, that is plastic modulus. As the plastic modulus that we just obtained here was 1037.18. So now we will be focusing on this column, and we'll be finding the value that is greater than 1037.18. As you can see, the value is mentioned in centimeters cube only. So we'll be seeing these values, and we'll be finding the values which are greater than 1037. We obtained two values here. First one is 1176.18, and the second is 1099. And for that you have to see here that it is mentioned that one is for ISMB 400 and other is for ISLB 400. Clear? So you need to remember this. We need to check also. After completion of our answer, we also need to check that the section we have provided is sufficient or not. And for that, you always need to assume either heavy section or medium section. Do not ever opt for junior sections or light sections. Clear? So here we will be always opting for either medium sections, that is MB, or heavy sections, that is HB. So out of these two, we are getting the value nearer to be in MB section. So we'll be assuming ISMB 400. So now we'll be taking the parameters from this case, that is from ISMB 400. We'll be trying ISMB 400 because we have still not proved that it is sufficiently valid or not. So we are just writing that we are trying the section. It is called a trial section. And if the checks are satisfied, then we can say that we can provide this I section. Okay? So we'll be requiring these quantities. Half of the quantities can be obtained from this direct page, and the remaining properties can be obtained from your steel table. So after calculating these properties, you need to find the section classification, and section classification is again given in the same page, that is page number 18, table number 2. So after moving on to page number 18, table number 2, the first thing will be to find the value of epsilon. Here Fi is mentioned as 250, so the value of epsilon will be 1. So now we'll be focusing on again two things, that is we'll be finding the value of flange, and then we'll be finding the value of web. So for flange again we'll be taking this section, that is rolled section, and for that the equation or the ratio will be B by TF. B, that is our half, so BF was 150, so B will be 70 in this case. So the value comes out to be 4.37, and as the value comes out to be 4.37, it falls under class 1, that is plastic. And now we'll be finding the value of our I section. In the column portion, we used this part or this row, that is for axial compression. Now we are designing for our beam sections. So for beam sections, we will be always using this row, keep in mind. Clear? Do not mix it up. We will be always using the first row for our beam sections, and for that the ratio will be the same, but the maximum limits will be different as compared to our column sections. So now we will be finding the value of D by TW, and D by T value comes out to be 38.20, and it is less than 80 for epsilon. So as it is less than 80 for epsilon, it will be under plastic section. In both cases, you will be always getting the answer to be plastic section only. Clear? Here ineffective area won't be coming into the picture because we will be selecting always ISHB section or ISMB section. So here the plastic section is classified. So now we will be finding the actual weight of our beam. So as we all know that we have founded the values of our factored load, that was for factored dead load and factored live load, but now we will be adding up the values of our I section. So the I section that we selected also carries some weight that will be obtained from our steel table. So that will be adding up, and then we'll be finding the final value of our bending moment and shear force. The previous bending moment and shear force was just according to the external load that was acting. Now we'll be finding the moment according to its or including its self weight. So the next step will be to find the factor load of our self-weight or the factor self-weight. So the self-weight of beam, that is for IS MB 400, this value can be obtained from our steel table. So factoring it, the answer comes out to be 0.923. So the factored dead load comes out to be 23.42, and the factored live load was same because the self-weight will be included in the portion of dead load, not live load. So the total load comes out to be 38.422. So now we'll be finding the value of bending moment and shear force according to this load. So the new bending moment and shear force will be this. Bending moment will be 172.90 and shear force will be 115.26 kilo Newton. After finding this, we'll be doing a small check, that is for check for susceptibility, that the check section we have provided is equal or sufficient or not. And for that, again we'll be moving to our section classification page. Here you can see in the note number 3, it is mentioned depths shall be checked for shear buckling in accordance with 8.4.2, that the equation we just saw, when d by t is greater than 67 epsilon. So if the values of d by t, that is TW, comes out to be greater than 67 epsilon, then we need to provide shear buckling. So we'll be just checking that we will be opting for shear buckling or not. In most of the cases, that is in 99% of cases, this value will always be less than 67 epsilon. We'll be just checking it out. So the d by t TW value comes out to be 38.2, which is less than 67 epsilon. Therefore it is okay, and there is no need to provide shear buckling. So moving on, we'll be finding the value of our design strength. So the design strength check can be according to page number 59, clause number 8.4.1. Here, as you can see, we need to find the value of VD. But VD equation is given as Vn upon gamma m0. Gamma m0 is 1.1, and the value of Vn can be obtained here. It is mentioned Vn equal to Vp. So we will be focusing on this part. So Vp is equal to AV Fyw upon root 3. Fyw, that is yield strength of web. Yield strength of web will be our Fy. AV, that is shear area, and shear area can be obtained according to this clause, that is 8.4.1.1. For I and channel section, we are always using I section, and we are using our hot roll section. So our shear area will be H into TW. Clear? So our final answer, that means after substituting the value of H into TW in the value A here, and after substituting the value of Vp here, we will be getting the final answer of Vd to be Fy upon root 3 gamma m0 into our shear area, that was H into TW. So solving it, we are getting an answer 467.12 kilonewton. So this is our design strength, or you can say design shear strength of our section. But as per our IS code, as you can see here, as per our IS code, it is mentioned when factor design load does not exceed 0.6 VD. That means we always need to take the value 0.6 VD, and then we need to check that the shear that we obtained is less than this value or not. So this was our VD value. So 0.6 VD comes out to be 280.27. So the shear force that we calculated after adding the self-weight of section should always be less than this value, and the shear value that we obtained was 115.16. As it is less than 280.27, therefore the section that we have provided is correct up till now. Clear? So this was check for our shear capacity. So now we will be finding our last check, that will be the check for moment, and for check for moment we will be moving on to page number 57, table number 14, and now we will be finding the values of FCR. In the previous section, or in the starting of section, we used to assume that the KL by R was 100 and H by TW was 225. Now we will be proving that what was our final value, and then we will be finding the value of FCR. So here KL by R, as it is not mentioned that the ends are either hinged, either pinned or anything, we will be always assuming the K value to be 1. Now this equation or this statement, that was beam is laterally restrained by cross beam framing at midspan. It is restrained at midspan. That means our beam is divided into two parts. Clear? The total beam was of 6 meter length, but as it is restrained at center, for effective slenderness ratio, we'll be taking the length to be 3 meters. Clear? So this statement is only applicable for KL by R consideration in the moment equation. If this statement was not given, then here the value will be 6000 that will be taking. Clear? This statement will be using just in the calculation of moment, as it is mentioned that it is restrained at midspan, so it will be dividing our beam into two parts according to effective length. total length was 6 meter. So considering the half of the length, it will be 3 meter, that is 3000 mm. So here we will be substituting this value. Do not forget, here do not mention 6000 meters, else your answer will be incorrect. So the answer here comes out to be 106.38. And next thing we'll be checking is h by tf. So h by tf here comes out to be 24. H here will be our total height minus the thickness of flange. Here it comes out to be 24. So now you need to do horizontal interpolation and vertical interpolation also, and then we'll be finding the value of FBD. So the FBD here comes out to be 157.45 Newton per mm square. Here the value of FBD. After finding the value of our FCR, we will be equating the value of FCR here, and then substitute the value of FCR, we will be getting the value of FBD to be 157.45. It is according to our interpolation method. And then we will be finding the value of our MD, that is our design moment. Ultimately that is given in our page number 54. So here, and the MD equation will be beta B ZP FBD. ZP, it will be for the section that we have provided, that is ISMB 400. Beta B will be always taking at 1 because it is mentioned here, it will be 1 for plastic section, and FBD we have just obtained. So the final answer here comes out to be 185.18 kilonewton meter. Here, so this value should always be greater than the bending moment value that you have provided after including the self-weight of section of I section. So it is greater than 172.9, which was the bending moment that we found out after providing or including the self-weight of our beam. So this is valid, and therefore the section that we have provided ISMB 400 is perfectly valid. So this is how you will be designing beam, that is our steel beam for laterally unsupported or laterally unrestrained beams. Clear? So this will be our today's exercise problem. Solve it, and in the next session we will be looking upon laterally restrained, or you can say laterally supported beams. Yeah? Thank you.